Hello, the last time we learned the basics about Thread, so different layers, network topologies, IPv6 addresses, the device types and the roles, and today we want to make a first practical example. For this we are using OpenThread. OpenThread is an open source implementation of Thread from Google. It supports IPv6, UDP sockets, core app client and server, DHCP client and server, border router, and we can configure it via a command line interface. It's also possible to using an API, but this we will learn later. Today we're only using the quite comfortable command line interface. This is for first practical example, quite nice. OpenThread is already supported by a lot of companies like Google, Nordic Semiconductor, Silicon Labs, Texas Instruments and a lot other. Today we want to use hardware from Nordic Semiconductor. Nordic Semiconductor has a chip, a microcontroller, nRF52840, which is quite powerful. It has 64 MHz Cortex M4 microcontroller, has 1 MB flash, 256 KB RAM and a 2.4 GHz transceiver unit integrated. It supports Bluetooth Low Energy, Thread, Zigbee and for us today is only interesting Thread, of course. Has like typical for microcontroller lot interfaces like an ADC, UART, SPI, two-wire interface. Nordic calls this chip also system on a chip or not microcontroller, because so many things are integrated like the transceiver and also easy direct memory access, but yeah, you can still call it actually microcontroller. Normally for programming an ARM microcontroller we are needing a programmer or debugger. ARM microcontroller using serial wire debug interface. You see here a J-Link interface. It's using two pins, a clock line and a data line, and ground has to be connected. JTAG, what we are using normally for like AVR microcontroller, using some 4 pins. Yeah, but 2 pins of course is more comfortable. But we don't need an external one because we are using a developer kit where this is already integrated. We are using the nRF52840-dk. Here on the side you're seeing the name. There's a chip here, the nRF52840, and we're having here a microcontroller, an ATSEM3U2CA microcontroller, and there's a firmware on it which works as J-Link and USB bridge. So we don't need an external J-Link, we just can connect here the USB port. The USB port is then directly connected to the chip here and depends on if it's in using the debugger or the USB bridge, and is then connected to the chip itself. Support has further on a few LEDs, a few buttons, a reset button here, and there is a second USB port here, but we are using the left one. Yeah, be careful. This one goes directly to the chip, and for using this we needing some to implement software here on the chip, and we don't do this at the moment. The switch from nRF only or default, this one have to be on default. If not, the left part is cut it off. Yeah, it's deactivated. The power switch is on the left corner, downer corner, and it has to be also on. And the power source switch we are setting to VDD. This is power. The power supply comes from the USB port. This developer kit you can get at Mauser or DigiKey for around $50 US. So it's not so expensive. So we need 2 from this because we want to make a network. So 1 is not enough, so at least 2. Next we're needing a development environment. For this we are using Seger Embedded Studio. See, here's a link for download. I will put all the links, of course, also in the description from this video. This has a compiler and a toolchain already integrated. It's also possible to use a GNU compiler directly with Make and an editor. That's not so convenient. And Nordic supports also EAR Workbench, but since Seger Embedded Studio is free for use for Nordic Semiconductor products, it makes sense to using this, and it's really quite comfortable. It supports Windows, Linux and macOS, so we are also not dependent on one specific operation system. The free license you can get under license.seger.com/nordic.cgi. When we're going on the website, we're seeing here Seger, the Seger website. We are clicking then on Embedded Studio and then on Download. And for non-commercial, it's anyway free, so we can use it. We just have to click a pop-up window away at the beginning. We are choosing our version for our operation system, mostly probably a 64-bit. We just download it and install it with the default parameter. Is always a good decision. Afterwards, if we want, we can of course also apply for our license. Yeah, we have to put in our name, company, email address, and what's important is the MAC address. This license is bound to one computer. Then we send it and we get the license key, which we have to add into the Nordic Seger Embedded Studio. The last what we are needing is a software development kit for our Thread applications. So Nordic Semiconductor have three types of SDK. The first one, nRF5 SDK, is just for Bluetooth Low Energy and it's a basic SDK. Then there is another SDK for mesh. This is for Bluetooth Low Energy mesh. It's also not the right one for us. For us, the right one is OpenThread integrated is nRF5 SDK for Thread and Zigbee. Here you're seeing the link. I will put it, of course, also in the description. When we're going on the website, we just click on Downloads and select the version 4.1. Just download it and save it at our computer. And afterwards, we just have to extract this folder. But when you extract the folder, looks like you don't put it too deep, don't place it on the desktop or something. Make it near to the root folder. Set the path names don't become too long. This can cause compiler errors later. Also avoid white spaces. There are a lot of folders in the SDK. The components folder, there is the basic like board-specific libraries, and also we're having the libraries for two-wire interface, for UART, for encryption algorithm, for buttons, and ADC, and so on. There are two more folders with additional drivers and software, like the legacy driver and integration, and in modules we're finding drivers for another use cases like the clock and so on. We have in external, we find the OpenThread stack, the libraries here, which is interesting. But for us, the most interesting folder is the example folder. Here are the basic example for everything for using the interfaces, like in peripheral, we're finding the basics without wireless connection. We're having here blink example or two-wire interfaces example here for the UART, for the ADC, and so on, basic examples. Then there are with BLE, central and peripherals. These are for applications for Bluetooth. It's also possible for multi-protocols or Bluetooth and Thread, but for us the most interesting is at the moment Thread. And we are going there and copy the folder CLI. This is the command line interface example. We just go in the example folder again, make a new folder for us, call it like my projects for example, and place here the applications. We have to look that it's the same deep like before, so that the compiler don't make errors here. Afterwards we're going in FTD, full thread device, in UART, since we are using UART for the output. So here we have to choose which kind of board we're having. Our developer kit is 10056 PCA 10056. So we're going in this folder. We are using the blank example, not with the master boot record. Maybe I will explain in later videos what's with the master boot record and so on, but for us at the moment not important. Here also there are a lot of folders which are not so important for us because we are using Seger Embedded Studio and not the GNU compiler or the EAI. So we just can delete the other one. We're having sensor config left, which includes the configuration file for our SDK and the project files for Seger Embedded Studio. And just then we open this, and we're seeing here on the left the Solution Explorer. We can extend here, for example, the drivers. These are also drivers which are included, which are necessary, and the libraries which are included. For us, the main program is the main.c. Make it a little bit bigger so that we can see something. Yeah, it's already working, the basic application like this, but it's a little bit complicated. We adjust a little bit so that we understand it a little bit easier. The first one, what we're seeing here in the main, we're having a log in it. This initialize a logger, which is helpful for debugging. We can say print out something. It's in this configuration it's outputted through the RTT, it's called real-time terminal. This is the debug terminal from Seger Embedded Studio, and when we're going into debug mode we can see there an output. The scheduler, it's a little bit confusing at the beginning. We need this because we have here an event-driven programming. This means when we push a button, then an event is called, and a callback function is called. And when we're having something to compute there, which needing a little bit more time, we are blocking through this also other interrupts with the same priority or lower priority. And of course we don't want this, then maybe we have a package lost or something of this because the stack is also hanging. So we try to put it as much as possible in the application itself, and for this is a scheduler. When we push a button and the callback function is called, we put another function with the basic code in a queue, and the queue is then called with the function here app schedule execute. So with this we're bringing the whole event in the application and not with the interrupt in the event handling. Afterwards we initialize the timer, which is necessary also for the scheduler and also for OpenThread. It's just initialization of the app timer. The LEDs in it, actually we don't need. Also this one, we don't want to use LEDs. This is just for status. It's not important for us at the moment. The thread instant in it we put in the front because I want to delete one of the while loops so that it's more clear, because we don't want to implement a reset button. It's not really interesting. And when I delete this all, you see it's looking already a little bit more clear. So finalize we also don't need. So then we're having only left the thread process in the infinite while loop and the function from the scheduler. When the thread processes are all finished and the scheduler execution is finished, then we look if there is still something in the logger queue, and if there's nothing, the device tries to sleep to save energy. And when the event comes, then the device will wake up again. We have to adjust here something in the thread instant init. We just clean also up the code. We don't need the finalize anymore. Here we also don't need the board specific functions, and also we don't want a callback which informs us about the state change in threads. Is also not interesting at the beginning. Here we just init then the thread with the basic configuration, and then we initialize also the command line interface. Here we have to adjust two parameters. Auto commissioning we're setting as to true, and the auto start we don't disable, we set it on false. This means when the thread is starting, we are the initialization starting, it's try also to start the thread network with the parameter which are already stored. This is auto commissioning on the microcontroller, so when it's not, the non-volatile memory is not empty and there are parameters stored for the network, it's taking the one from this. We have to be careful there. We have to delete at the beginning the whole chip that there is no confusion. And when, sometimes better to erase the whole chip also. When I have from another thread network, the data still stored there, then it's used from them, and then two devices are not finding each other, for example. We will see this when we transfer the data. And also we want, of course, the auto start enabled. When there are no parameters stored, it just takes a default parameter. So let's init we can also delete, and the thread state change also not important. So it's already a little bit smaller, the program. We just build it, and afterwards we transfer to our devices. I have here two devices. This was, of course, now try it again. So here you're seeing the devices, the developer kits, the left and the right one, and now I have to transfer it to both of them. I can use the same code for them, but when I transfer it now and I go on target connect JTAG, we see here that I have two devices and I don't know which one is which one. I can just choose now one, it's no problem, since I will anyway transfer both to the same software. But when I look at the chip, at the J-Link chip, then there is a number, the serial number. This is the same number which we saw here in the identification, the USB identification. So we can we know which device is which when we transfer something. When we're making different source code for them, of course it's important. Here it's now not really a problem. So we just go then on target erase all, like I described before, so there is nothing in the non-volatile memory anymore. Not the parameter before, and then we just download this software, the application. We do the same with the second device. Also erase all and then just transfer it. After transferring the firmware, the thread network is already started, but for communicating with our devices we're needing a terminal program. I'm using here now PuTTY. You can download it from putty.org. It's quite simple telnet client. You can of course also use HTerm or whatever. We need to know the COM port. In Windows we find it over the device manager. We see here my devices are having COM port 3 and 4 for the J-Link. With your computer of course it can be different ports. We have to choose the baud rate, which is 115,200. Hardware flow controllers off, parity bit off, and stop bit we're having 1. I just starting then PuTTY, and you see here COM3 and 150,200 for the speed. The further parameter you find under serial, but there are defaults, so we don't have to change them. Yeah? Just open, and then we're seeing here our window for the COM3. Just clicking enter and you're getting the prompt. Now you can enter the commands, like the first command is state, which state it is, and I just connect it to the leader. I do the same with the second device on the COM port 4, and also enter and state, and it shows me it's a router. So whole list of commands from the command line interface we find under this link, github.com, OpenThread, and so on. And yeah, there are really a lot of commands we are seeing here. Yeah? We can let's see the child's extended address, extend PAN ID, and so on. You can set there's a whole parameter for the network. For us at the beginning we are using only a few commands. The first one is was the second one, an IP address. The state just shows us the role of the devices. The IP address shows us all IP addresses. Just try it, IP address, and then here we're seeing there are 4 IP addresses. The leader having 4. The downer one is for link local communication for direct neighbors. The unique IP address here is the third one. We're seeing here is 64-bit in the front is the mesh prefix, which is similar, is the same as the 3 first IP addresses. The second one is then the airlock. When I look, this is the airlock for routing. Yeah. When I look at the second device, it's similar, just there are 3 addresses. And also the local link. Here's the unique addresses, mesh address, and here we're having the airlock for routing. So the next command is data set active. It shows us the parameter from the network, like the channel mask, the extended PAN ID, the mesh local prefix, the master key for the encryption, and so on and so on. It's of course the same with the other device. If not, they wouldn't find each other. Same channel mask, mesh local prefix, and PAN ID, and so on is also the same. Last, we want to send an UDP-package from one device to another. For this we have to find out, of course, the IP address from the first device. We have to make UDP open. Then we bind the device, but we have to bind it through IP addresses. I forgot here 2 colons. You will see this shortly. Then on the second device we have also to open the UDP, and then we just send the package to the IP address, to the port which we bind before, and send the text what we want to send. So let's see how it's working. So IP address, then the UDP open, then the UDP bind, 2 colons for the IP address and the port, and then on the second one we just open the UDP, then UDP is sent, and then I copy the IP address. We are using the unique IP address here. I don't use as airlock. We would also work, but it's not really good to use this IP address since it can change with the network topology. Then we're sending the text and putting it enter, and we're seeing that 5 bytes are received from this IP address here, and the text hello. This was our first practical thread example with a command line interface. I hope you like it and understand it. In one of the next videos I will show you how to program thread over the API, since with this it's quite nice for playing around and for analyze, but how we can control now a sensor and sending the data, it's quite complicated to transfer to an UART and maybe connecting another module or something like this. So it would be nice to be able to program it over the API. But the next video I will make a video about sniffing the thread network, so that we can also analyze and looking what we are sending in the thread network. It's helping us also a lot when we're programming and when there's a problem to see what packets are really sent and which are arrived and so on. So see you for the next video.